Hi, this is Greg from Structural Toolkit, and this is the fourth video in our two-story residential house design series. In our previous video, we went through our upper roof and wall framing design, and now we're up to our floor and lower roof. A lot of the concepts we covered in our roof framing video are also going to be applicable to our floor framing design. If you feel you're not fully understanding any of the concepts in this video, such as spans, restraints, and the way we approach loads, it may be worthwhile to review the roof framing video. A floor framing design is typically going to be a bit more complex than the roof above that it is supporting, so there's going to be a few more things we'll have to think about as we go through the design. The way we'll want to go about our floor and lower roof design is to start with the roof joists and roof beams, and then go into the floor joists and each of our floor beams. The order in which we'll design each of our beams will depend on its load paths. For example, if we have a floor beam that supports another floor beam, then you would want to design the supported floor beam first so that you will have the reaction calculated for the point load on the supporting beam. Finally, you'd then design any lower roof lintels, as they will often support floor or roof beams and will typically always be supported on columns. With all the beam members designed, you could then design the lower columns. The overarching idea here is to start with the members earliest in the load path chain, as we try to transfer the roof and floor forces down another level. So before we can get into the floor framing itself, we'll need to start with our lower roof design. We can first cover our joists, or our roof rafters as they are commonly referred to. In our Structural Toolkit project that we've been working on, we'll first want to create our lower roof section to the left. With this section active, we'll open up a roof beam design and name it Roof Joist RJ01. So our roof joist design is going to be similar in nature to a lintel design we did in the previous video, as in general terms it's going to be carrying similar types of loads. As our roof joist is going to be a repeated member, we'll be setting our category as 1. Our span is going to be from centre to centre of supports, which if we measure on our drawings is 3930, so we'll round this up to 3950. Roof joists are typically spaced in the roof at either 900 centres for sheet roof or 600 centres for tiled roof. These aren't concrete values however, and so you can adjust the spacing as necessary to suit your design. A good case of this is where there isn't much depth within the roof to fit roof joists, and so you reduce the spacing in order to help reduce the member depth. That being said, wherever possible it's going to be better to stick to the standard spacings. As our roof will be sheeted, we'll use a spacing of 900. So typically with a roof joist system like this, the roof space will comprise of the roof joists, which have roof battens fixed perpendicularly to the top, and then ceiling joists underneath, which may be hung or fixed directly underneath with then plaster at the bottom. There are also cases, though more often with trusses, where there are no ceiling joists at all, and plasterboard is fixed directly underneath. With that in mind, we can understand that our LAY here is going to be our roof batten spacing, as they will be sitting on the top of the member. For our residential house, roof battens are usually spaced no more than 1200 apart, so we'll use 1200 here. To keep things consistent and to prevent any confusion later on, we'll be using the same roof dead load as we did with our upper roof lintels, being 0.4 kPa. As we will also be including the self-weight of the joist itself in the design, this is somewhat conservative. Our live and wind loads have already been calculated for us, and so we don't need to add any more load inputs to our joist. To keep things clear, we'll be deleting any cell inputs that serve no purpose. Just as a reminder, our ultimate wind load input has been determined by our wind load project value we set up in a previous video, just like the house input to the top right. As we went through in our previous video, our order of timber grade preference is F7 Katy Pine or MGB10, then F17 KD hardwood, and finally LVL15. When timber doesn't work, you'd then go for steel. In the case of floor and roof joist, steel really isn't an appropriate choice, however, and so in that situation you'd need to revise your beam layouts, unless you plan to use something like light gauge steel. If we first look at F7 KD pine, we can see we'll be able to get a 190 by 45 to work. Like the previous video, we'll be aiming for span on 300 for deflection. We briefly touched on it earlier, but the available depth within a roof structure is a key aspect to think about when selecting a timber size. This can be particularly critical when the roof joist needs to fit under a box gutter. In our case, we can see we have a box gutter on the southern end of our roof joist. We'll say that the architect has advised or provided us with a section showing 150mm of space underneath for any structural roof members. So this means our 190 joist will no longer fit. What's typically done here is the end of the roof joist will be notched down to 150 along the width of the box gutter. AS 1720 provides some design guidance for notching a timber beam in Appendix E9. Though an important distinction to make here is that the design capacity is for when there is a downward shear force and the notch is on the top of the beam, or vice versa. The idea here is likely due to the failure mechanism being calculated for, that is, the fracture of the beam at the notch interface. We talk about this more in our timber notch design video. As our notch is going to be on the top side of the beam, we'll then want to be using our wind shear force, as this is the only force that would apply upwards. To design this notch, we'll open up a timber member design. We'll then go to the notch section below, and we'll also select our current timber size. We know our box gutter is 300 wide, so that will be the length of our notch. We won't have a taper, and we know the depth of our notch will be 40mm. Finally, we then have our force values, which for shear will be our wind ultimate shear force of negative 0.61 kilonewtons. As the notch isn't directly at the support, we should probably consider some moment, which we can calculate by multiplying our reaction by the lever arm of 300, and minusing off our UDL on the beam, multiplied by the lever arm to the power of 2 on 2. So to show that in action, we'll go negative 0.61 times 0.3 plus our UDL of 0.31 times 0.3 to the power of 2 on 2. This then gives us a moment of negative 0.17. We can see that our notch works with these loads. Technically, we could also reduce the shear force we used, as it will be slightly less at the notch interface, but we'll leave ours as is. Another thing we could have also looked at is refining our wind forces on the joist design, or adding a taper to the notch, which can significantly help with capacity. Now, although we've done the design, we'd also then want to ensure a note or similar is included on our drawing to indicate this notch. Note that you can also do this notch design using a linked member design, and it may make it a bit easier to work out some of the forces. Our next design would then be our RJ2s, which can be designed using the same process as our first choice. So we'll skip ahead to where we've designed our single roof beam. Here we have our roof beam design completed. As the span was shorter than 2 times the spacing of the roof joist, we have adopted the point load approach, something we discussed at length in our previous video. Our design has resulted in a 120 by 45 pine. This size is purely a minimum required, and so the builder may opt to use a 190 instead to match the joist depth and possibly make it easier to construct. With the design complete, we can now move on to our floor framing, as we'll now have the RB1 reaction ready for when we design our FB6 that's adjacent. So in a similar way to the roof framing, we'll start with our floor joists. Floor joists in a residential first floor will often be floor trusses that are designed by a manufacturer, as a system like this is often preferred. You may then still specify a solid timber joist as an alternative, which is what we'll be doing. So to keep things organised like the rest of our project, we'll create another section and call it floor. To design a floor joist, we'll want to use the floor beam design module. So we'll open one of those and call it floor joist FJ01. We'll want to start with our longest spanning joist, which will be the joists on the northern side. And if we measure from centre to centre of support, is 3950 rounded up. In our design, we'll set it as category 1. Typically, centres for floor joists are 450mm, which we'll go with. They'll also be single spans. Although we do have this FB1 here, typically due to depth restrictions, the joist will fix into the face of the floor beam, so double span here isn't really an option. Finally, we have our LAY top restraint. Usually there will be some form of yellow tongue flooring that is nailed to the top of each joist at intervals along its span. A good space in here to represent that might be 600, which is what we'll be using. With our geometry sorted, we can move on to our loads. A floor structure like this will often comprise of particle board on top with the joist underneath. Fixed to the joist will be the ceiling structure below, that's then plastered. In the floor, you'll also usually have more services such as sewer and water pipes than in the roof. A commonly used value to represent all of this is 0.5 kPa. Like with roof joists, this is going to be a bit conservative as we are already going to include the self-weight of the joists itself, but helps keeps things consistent throughout the design. As for our live load, we'll be using the 1.5 kPa along with a 1.8 kilonewton alternative point load, which comes from AS 1170.1 for a self-contained dwelling. Those are all the loads we'll be adding, so we can delete anything else we won't need. Having a look at our member size, we can get it down to a 240 by 35 F17 without exceeding any of our standard checks. However, there is a warning to the right to do with vibration. This isn't something that comes into the roof beam design. AS 1170.0 recommends for floors that the midspan deflection caused by a 1 kilonewton live point load should be less than 1 to 2 millimeters. This check is incorporated into our floor joist design, and we can see at the moment that we're at 2.3 millimeters deflection, or in other words, vibration may be an issue. So what we'll do is bump it up a size to a 45 thick member, which brings it under 2 millimeters to 1.8. Now that we've dealt with this, we can use the option to the bottom right of the module to turn it off. Otherwise, someone checking it later on may question it. Now, when looking at a floor joist, this 1 kilonewton point load will distribute into adjacent members to some extent, so you might be able to accept a higher vibration limit. Refer to AS 1720.1 Appendix E8 and AS 1720.3 Clause 4.1.3.2 for more on this. As an example, the AS 1684.2 supplements allow a 240 by 45 F17 hardwood floor joist at 450 centres to span up to 5.2 metres. At this span, a 1 kilonewton point load results in a deflection of 4 millimeters, suggesting a sharing factor of around 2. That then completes our first floor joist design. Something you may have thought about is that there are also going to be internal non-load bearing walls that will sometimes sit on our floor joists. Usually what is done here is a double joist is provided. To show this in action, we'll copy this floor joist and demonstrate. A good value for an internal plastered wall is 0.4 kPa, and our floor to ceiling in our case is 2700. We'll then change our member to double, And we can see that by providing a double joist under the wall, there aren't any issues. Our next floor joist, FJ02, would be designed in the same way as we have for FJ1. So we'll skip ahead to our first floor beam. Our first floor beam, FP1, is quite long in span, but load-wise is going to be fairly straightforward. Loaded onto it are floor joists on both sides of the beam. We'll open up another floor beam designed in timber and call it FB01. Measuring the span gives us a span of 6,700 rounded up. This is quite a long span, and so we're probably not going to get this to work in timber. When something like this happens, it's always good to think again about our beam layout, as it may be more appropriate to frame it in a different way. In our case, one option we have is splitting this long beam up by providing a perpendicular beam that lands on L9 in the north and the corner of this internal wall next to the kitchen. This will reduce our FB1 span down to 5,100 and likely reduce the beam required by a few sizes. The only problem is that we'll end up with a new floor beam that spans 6 meters, so likely another steel beam. As it's going to be supported on L9, L9 may also have to increase in size, and although we have a column at the other end, this column doesn't land on an internal stiffening beam at the moment, which isn't ideal. So it's probably going to be better to leave our FB1 as it is. To a bit better demonstrate the design process, we'll pretend we don't know yet that it won't work in timber. With our span already in, next is our centers, which will be half the joist span either side. This measures at 3,650 rounded up. Our restraints along the beam will be at 450 centers, being the spacing of the joists. Our floor load is 0.5 kPa, and as we do have a bit of internal wall that will load up onto this beam, it might be a good idea to include that load as a UDL over the span. So we'll include 0.4 kPa of 2.7 meter wall. And finally, our live load can be left as is. Right away you can see our beam is really struggling. We'll go up to our last timber option of a LVL15. We can see with just one 360 by 42, we're still nowhere near acceptable. If we make this a double and keep going up, we can see we're not going to be able to get it to work even with a double 400. Around about this point, you'd want to transition into steel. So rather than creating a new steel floor beam and manually entering all the values, we can just convert our current design to a steel beam by clicking the Timber to Steel button on the Member tab. We'll delete our original in this case. As always with this feature, we'll want to make sure all the inputs are correct. There is also the alpha M that will need to change as necessary. As we are dealing with small segment lengths, we can keep it as 1. So the go-to steel member we'll be wanting to use wherever possible is a PFC. Not only do PFCs usually fit nicely within walls and floor framing, they're also fairly easy to fix other members to and vice versa. If a PFC doesn't work, then you would maybe start looking at UBs or similar. We'll start off by selecting a PFC. We can see that a 250 PFC works with our usual checks. However, something to keep in mind is the amount of deflection in millimeters. Floor joists are going to be fixed onto this beam, which already deflect a certain amount. If the beam it is fixed onto also deflects, then the end support of the joist at this point of deflection will also move downwards, effectively increasing the overall deflection of this joist. The concept here is effectively cumulative deflection. It's an extremely important aspect of design to consider, and it isn't captured in our individual designs due to us having simplified the approach down to isolated single span beams. A good approach then might be to limit our total deflection to 15 millimeters, so we'll bump up our beam size to a 300 PFC. With that done, our first floor beam design is complete. Our next floor beam design is a little different. FB2 has some floor joist loads like with our FB1, but it also may need to support some stair load depending on how the stair builders decide to frame the stair. Usually a stair like this would have timber risers and treads that form the steps, which are then supported on either a wall or an external stair stringer. In our case, they may provide a stringer that sits straight onto the wall, or they may fix it into our beam. To ensure we've accounted for the latter, we'll be including a stair point load in our design. So we'll open up a new timber floor beam design. Our span is 2,350. Our centers will be the load from our FJ2 being 600. We'll remove our alternative floor point load as we'll be applying one from the stair. Now to work out what our point load will be, we'll first need to determine a load area. So it's likely the stringer will be supported at the stair landing, which starts about here. So we can go halfway between the stair landing and our FB2, and then across will be halfway to the wall. So our area will be something like this, which we can see equals 0.416 meters squared. We'll then multiply this by our 0.5 kPa dead load, and for the live load it will either be 2 kPa or 2.7 kilonewtons as per AS 1170.1, where in this case 2.7 kilonewtons will be critical. To make it clear what we've done, we'll right click and go insert comment from cell. The point load is about central, so we'll leave the position as is. Looking at our member size, we can see it will work as a 190 by 45 F17. And with that, our second beam is complete. We spoke about it in the previous video for roof beams, where the shear using point load at support defaults to yes. For floor beam design, it defaults to no, as typically with floor designs, the engineer is going to know where the point loads from, say, other floor beams will end up being. So for our next beams, FB3 and 4, they are similar to our FB1 design, so we'll skip past those. FB5 is also similar, but has a few extra loads on it that will be worthwhile to look at. So we'll skip to the point where its design is complete and have a look. Here is our completed FB5 beam design. We've got a floor load on one side and a roof load on the other at this level. But something we also have is an external load bearing wall. We can easily tell this wall is load bearing due to the hatch we added during the setup phase. To properly design this beam, we've then added a wall dead load along with additional roof load to account for the width of the roof that this wall supports above, and also the lower roof load. To keep things clear, we also added a comment about this. When designing floor beams like this, you'll need to be constantly thinking about the different kinds of loads that may be on the beam. And so by setting up our drawings in the way we have, by including hatch for load bearing walls, and also showing any columns that come from above in their own color, we've made it quite easy to work out where all our loads go. Our next beam is then FB6, which is going to be much more complex than the beams we've designed up until now. We can see we have both FB5 and RB1 supported on it at the corner of the upper floor. It also then supports the end wall of the upper floor, but not for the entire span. We also have some columns coming down from an upper roof lintel. So effectively we have several point loads at different locations and also a variety of partial UDLs across the span at different segments. When it comes to supporting columns of lintels, you can sometimes justify idealizing their loads into a UDL, but given the spacing of each end column, it probably isn't very appropriate in this case. This kind of design is going to be more suited to a linked analysis member design, where we'll have more options on what we can do with our loads. If you're unfamiliar with this approach, it would be worthwhile to have a look at our beam design video. Given the length and amount of load our beam will be carrying, along with already supporting a steel member, we'll be designing it in steel. So we'll start by opening a steel member design. With our member design open, we'll then open up a linked analysis. We'll start by putting in our span of 5,750. Our span type is simple and our live load type will be floor. So we can then move on to our loads. We'll go from left to right, so starting with our full span UDL input, if we look at our plan, we can see that the only consistent load we'll have across the entire span is some amount of roof. As the roof joists don't span into the beam, the most load you get on it is the centres of a joist, being 900. Although technically the southern part isn't even 900, going halfway to the garage lintel, to keep things simple, we'll use 900 centres of roof along the entire span. So in our UDL input, we'll go 0.4 by 0.9 for our dead load, being 0.4 kPa times 900 centres. And then in our live load, we'll go 0.25 kPa times 900 centres. To keep things clear, we'll also add a comment stating where our load comes from. Our next UDL is then our wall dead load. Measuring from the top of the floor to the top of the window, we get about 2400. We do miss a little bit of the wall in the corner here, but given we're being conservative in many other areas, this will be okay. Measuring the length of this, we get 3950. So in our start, we'll put 0, and in our end, we'll put 3950. In our dead load input, we'll put 0.5 kPa, as it is an external wall, times our 2.4 metre height. As this is also where our floor will be, we'll also put in 450 millimeters of floor being one joist spacing. For floor, we have 1.5 kPa live load. That covers all our UDL loads. Next, in our point loads, we'll want to add our reactions. Our first two reactions will be from our upper roof lintel, being UL03. So in our reaction cells, we'll highlight the first reaction input, find our UL3 and insert the left reaction. Next is our right reaction, which we can do the same thing for. Our final reaction will be the combination of both our Ep.4 and RB1, so we'll add these in as well. You can quickly input a reaction by typing the member's name and then hitting tab, as we have been doing for all our reactions here. If we measure on our beam, our positions are about 100, 3150 and 3950. At the moment, we have quite a number of comments spread out over our page. So what we can do to tidy things up a bit is, instead of having these comments, we can just name each of the point loads accordingly. PL1 will be UL3 left. PL2 will be UL3 right. And PL3 will be Ep.5 plus RB1. And with each load named, we can delete the comments. Next, we can switch back to our design document and bring in these forces. We'll start with our max M star positive. Before looking at our section size, we'll need to work out what our segment length and Ep.4 will be. To keep things simple, we'll set our segment length as the maximum distance between our point loads, which is about 3050. Looking at our bending moment diagram, our Ep.4 will roughly equate to somewhere between 1.3 and 1.75, which we can get an idea of from looking at the Ep.4 tab of the design module. We'll pick the conservative option for now and see how we go. There are also options here for determining the Ep.4 using the formula from the code. With steel design, you need to always think about the various segments you have in your beam. As it's not always the case, the longest segment is the critical segment, particularly when you try to refine your Ep.4. So we'll see what PFC we can get to work with this force. With our max M star positive selected, we can get a 250 PFC to work. We'll also want to check that our shear force works, so we'll click the max V star, which we can see works fine as well. Typically for these long span beams, the bending moment and deflection is what will be critical, but it is still best practice to always check the shear. With that done, our floor beam design is complete. Having a look at our remaining beams, they're all going to be fairly straightforward. Each of these beams will be loaded with floor, lower roof, upper external wall and upper roof. Although a few of these have columns coming from above, as the spans of these upper lintels aren't too large, you can probably justify just idealizing these loads into a UDL across the entire span. We'll then skip ahead to the end of our floor beam designs. With all the floor beams designed, the next step will then be to design all our lintels. As we have brick veneer walls on the ground floor, there are going to be two components to this. We'll need to design both an internal stud lintel to support any loads from above, and also an external steel angle lintel to support the brickwork above the window or opening. We'll start with our external brickwork lintels first, as if an isolated angle lintel doesn't work for one of our lintels, we'll then need to fix it onto the inner lintel. So with that in mind, it makes more sense to do the outer lintels first. Before getting into designing our brickwork lintels, it's going to be worth mentioning that AS 4773.1 for masonry in small buildings does provide a useful table for specifying brickwork lintel sizes, being based on span, height of brickwork above and some other load types. This table does require the lintel to be propped for at least 7 days, so there is likely an element of arch in action that is incorporated into how these member sizes were originally determined. For our design, however, we'll be designing them ourselves. Although this table is applicable in our case, it will be a worthwhile exercise to demonstrate how to design them manually. We won't be considering any arch in action, and so we can expect our members to span a bit less than the ones in the table. For our steel angle lintels, the sizes we'll be looking at is something between a 90 by 6 equal angle up to a 150 by 90 by 8 unequal angle. We'll want to avoid 10mm thick members so that the builders can still feel some grout in between the bricks and the lintel. The easiest way to go about this is to work out the maximum span a 90 by 6 equal angle can go with our standard heights of bricks above our windows and openings. Looking at our elevations, we can see most windows have 900mm of brickwork above them, so we'll start with that. To begin with, we'll create another section to the left. And open up an angle lintel document. For now, we'll keep the name as a placeholder, as we'll be including its maximum span and its name at the end. As for our loads, the brickwork of a brick veneer is non-load bearing, so our lintel will only have brickwork on it. However, for good measure, we'll also include the alternative point load for roof in case someone hangs on or stands on the edge of the parapet above. Brickwork is 2.2 kilonewtons per metre height for one skin, so we can leave that as the default value here and put in a load width of 900. We'll then delete our UDLs for roof and put in our live load point load of 1.1. We'll select our 90 by 6 equal angle. Brickwork generally requires a lower tolerance of deflections, and so we'll be aiming for a span on 500 for dead load and span on 360 total. So we'll start slowly decreasing our span to meet this and the design capacity checks. Skipping ahead, we've arrived at 1750. What we can do now is keep going up a size and work out what span will work for each. We'll then rename the member to have this span included in the name. Using standard sizes, you will end up with 5 different types. There are a lot of different ways you can do this, however, as on certain projects there may not be many lintels to design, so you might just design each lintel as their own angle lintel design. You will also need to remember to design any lintels that have a different brickwork height above, such as our L6, which is a mid-height kitchen window. By the end of this process, you'll be left with lintels that won't work with one of the standard sizes, so you'll need to design them as a PFC and angle or PFC and plate using the modules we have on the desktop. You'd use these modules in a similar way to how you design an internal stud lintel, which we will go through shortly, but you'll also include the brickwork height as a dead load. Something important to remember with this design is you'll need to think about any torsional effects, particularly for larger spans with a significant amount of brickwork above. You may need to provide a plate welded to the flange ends to provide enough torsional capacity. We'll skip past this part of the design as it will be something we'll touch on in our next video, where we cover our brace frame in the garage being GL02. So we'll rename our first angle lintel here and then skip ahead to all of our other types already designed. Next is our external lintels that sit on the internal stud-work. Now, unlike the upper roof lintels we designed, our lower roof lintels are going to be a mix of floor and roof beam designs, where which we choose will depend on the type of loads the lintel supports. For example, we can see our lintels L1 and L2 are going to support some amount of floor, so they would be designed as a floor beam. But for our lintel 3 to 6, they are only supporting roof, so we'll design them as a roof beam. Not only are each of the module types tailored for their member design types, we'll also ensure we're using the correct size factors. At this point, the process of designing these lintels is probably clear enough, so what we'll do is skip ahead to where we've got both a roof and floor lintel design complete. Here we have both L2 and L3 complete. L2 is a floor beam that picks up Ep.4, along with floor, wall and roof loads. Something interesting about this design is that as the Ep.4 point load is close to the support, it has become a shear critical design. L3 is then a roof beam design, which due to its span being less than 2 times the spacing of the roof joist, we've designed with a point load. This is something we discussed in the previous video. As for a beam of a span like this, putting a point load in the center is going to be more critical than having a UDL over its entire span. The rest of our lower lintels can then be designed using the same process, though keep in mind some of these lintels will end up being PFC angles as we discussed earlier. We're now up to having all our lintels designed. You can see also in our project pane that we designed a angle lintel specifically for LO6 with the different height brickwork. Now before we head on to our columns, being the last part of our design for this video, we need to consider the fact that our L6 window is quite shallow, and so the distance from the underside of the window to floor level isn't insignificant, and so we'll probably need to consider wall tie action on the bottom plate under the window. This can be done in the same way we did on the previous video for the wall tie action under one of our upper windows. Skipping ahead to where this design is complete, we can see that a single bottom plate wall tie works fine, so we can move on having been satisfied that standard framing will do the job. Finally, we then have our columns. The process here is much the same as our upper floor, however this time we'll have a few extra column types. In our roof framing video, we spoke about using a DS1, which is a double 90 by 45 MGP10, and a DS2, which is a double 90 by 45 F17. We'll also be looking at using steel columns here to support any steel beams. Our go-to column size will be an 89 by 3.5mm square hollow section, which we'll call C1, and then increase the thickness of this column as needed. We're using an 89 as it fits nicely inside 90mm stud-work. What we'll then want to create is various column designs using our 3-meter floor to ceiling height, and work out the max load allowable for each type. As we have both floor and roof loads, we'll also need to consider roof and floor supporting timber columns separately, due to the psi values and K1 factor used in timber design. So what we'll end up with is a DS1 roof and floor, DS2 roof and floor, and then at least one steel column. We'll skip ahead to our timber column designs being done, as we covered this in our previous video. With our timber columns complete, we can see we have 4 different types, each with their own capacities. Next is our steel column. We've done a video on this module previously, so refer to that if anything is unclear. We'll call our column C1, input our length of 3 meters. As our columns are going to be framed into stud-work, we'll leave our K factors as 1 and our alpha M as 1.75, which represents the moment distribution we'll have caused by the eccentric point load induced moment at the top of the column. Unless we're designing for a propped beam where the beam will span over the column, we'll want to pick our end connection as face. This will give us a capacity of 21 kilonewtons for dead and live. With all our columns designed, we can now look at assigning these columns to the ends of all our beams. We'll do the same thing with our columns here as we did with our upper roof, where we'll create a plan on CAD that shows all the reaction loads we have on each column, and that way we can one by one assign the correct column. So here we have our plan with all our loads, and then a legend down the bottom for each column type and its capacity. We've already gone ahead and assigned all our columns, keeping in mind also that any steel beam will be supported on a steel column. Now when going through this process, sometimes either just the dead load or live load will exceed our column's capacity. For example, a floor load reaction of 10.5 kilonewtons dead load and 9.5 kilonewtons live load will only exceed the dead load component of our DS2, which has a capacity of 10 and 10. These are currently working loads and will be factored up by 1.2 dead load and 1.5 live load. With that in mind, we know that if we have 0.5 kilonewton dead load more and 0.5 kilonewton live load less, then our ultimate axial compression will be less than if we had just 10 and 10. However, something to remember with timber is that depending on your load duration, your capacity will change. For example, with the dead load only capacity, our K1 duration factor is 0.57, being much less than a floor duration K1 factor. So to be certain, you'll want to double check any column loads that don't conform with your design for maximum loads. In the event that this additional check doesn't work, you could possibly look at the design in more detail. For example, if this load is due to 2 different beams landing on the column from 2 different directions, you could consider the fact that the moments caused by eccentricity may counteract each other. As with most components of this project, there will usually always be ways to refine things down as necessary. At this point, we're now up to our brace frame design, which we will cover in the next video. But something we haven't spoken about yet are any of our steel beam and column connections. Other than the brace frame, which we're not going to do in this video, all our connections are going to be of simple construction, and so will not be transferring any moment. The way this is done with beam to beam or beam to column connections is by using a cleat plate that is welded to either a column or the web of a beam, and then bolting the cleat through the web of the supported member. As the majority of the moment in a standard section is transferred through the flanges, we can idealize this connection into one that does not transfer moment. This also aligns with the fact that we designed all our members as pinned and supported. Now, although you could go ahead and design each individual connection in a project, for a residential house it is typically more appropriate to provide a fairly uniform set of connections throughout all the framing. This approach will make it a lot clearer during construction and will require less details in the drawings and also less design work. For PFC beams like ours, one approach might be to provide two M20 bolts with a 10mm cleat for all PFC beams to columns or other beams, and increasing it to 3 M20 bolts where the PFC size is 300 or larger. One of the biggest beam reactions in our project is Ep.4, which to demonstrate will design its end connection using the cleat module. We'll skip to the end of the design, and so if you want to know more about the module, have a look at our steel cleat design video. Here we have our cleat design with the 30 kN reaction and 2 M20 bolts. For demonstration purposes, we'll reduce the bolt size down to 16, which we can see still works. But as you could imagine, some other 250 PFC beams may have a greater reaction that is larger than our minimum shear design force. There certainly is the option to maybe specify M16 bolts for smaller PFC sizes, but you will need to validate that these connections will still work. For our design, we'll be keeping the M20 throughout. Another connection you would need to look at the design of is timber beams that connect to steel columns or steel beams, like our Ep.4 connection to our C1 here, and in some situations also timber beams that connect to other timber beams. Typically you would provide a steel seat or cleat with bolts going through the timber member. We won't be showing how to design that in this video, so if you are interested you can check out the video we've done previously on the topic. As all other standard timber connections are covered in AS 1684, that about covers everything for this video. In our next video we'll be going through designing a residential brace frame, where we will be using Structural Toolkit analysis together with some of the Toolkit design modules. If you have any questions, feel free to contact our support team via email or by calling us. Thanks for watching.